Okay, so here is a hypothesis test for a single population variance. The assumptions here are similar to that of the confidence interval for population variance. In fact, they're the exact same. That we have a random sample from a normal population, and that we can't skirt over this assumption even if we have a large data set. All right. I do want to point something new out to you, though. If you look in table 712 of your book, you see the non-normality, the effect of the non-normality on testing the variance. And basically, what that table shows is a simulation study that suggests when the underlying population is not normal, is far from normal, then the actual significance level of the test is much different, or can be much different, than the specified level of 0.05. And so you'll want to look at that in the discussion from that. Basically, warning you to not use this method if the population is not normal. Okay. So the kinds of hypotheses that we can test here, well, similar to what we've done with a population mean, we can test to see, is the population variance less than some specified value sigma naught squared. We can test to see if it's greater than some specified value sigma naught squared. We can also test to see if it's different. Okay, so we have these familiar testing scenarios. The test statistic for us is basically that quantity, that ratio, what some call a pivot quantity that we looked at in the theorem that was used to develop the confidence interval formula for sigma squared. What we do here is we take n minus 1 times s squared over the null hypothesized value of the population mean, and that is our test statistic. It follows a chi-squared distribution. Let me make sure that's clear, which follows a chi-squared distribution. Chi-squared distribution with degrees of freedom n minus 1. Okay, so that's our test statistic. The rejection region depends on the particular hypothesis test that you're looking at. If you're doing a right tail test, you're going to reject if your test statistic is larger than some upper tail value that's specified from the chi-squared distribution. Okay, if you're looking at a left tail test, you're going to reject if your chi-squared statistic is less than some specified chi-squared percentile. And if you are dealing with a two-tail test, you're going to reject if the chi-squared is bigger than some chi-squared value or less than some chi-squared value. Now that the chi-squared value has, in this case, alpha over 2 in its right tail and alpha over 2 in the left tail for the lower tail percentile. Okay, so those are intuitive test statistics. If you look, say, just for example, at the right tail test scenario, if if in fact the alternative hypothesis is true, that sigma squared is bigger than sigma naught squared, we would expect to see a sample variance that's also much bigger than sigma naught squared. Well, that would be reflected in this quantity here being large. Okay, and so that's why we reject H naught in the right tail test if our chi-squared test statistic is large or is bigger than an upper tail percentile. Okay, coming back to this example dealing with the 10 millimeter bolts, suppose that it is determined by the manufacturer that an acceptable standard deviation for the bolt diameters is one that is less than 0.09 millimeters. We want to test this at the 5% significance level. All right. Can we conclude that sigma is less than 0.09? That's the question here. And so we are testing, in particular, our hypotheses look like this. Is sigma less than 0.09? That is the alternative hypothesis. The null hypothesis is that is sigma greater than or equal to 0.09. And I could rewrite these in terms of their variances if I wanted to. This would be sigma squared less than 0.008 just by squaring both sides. This would be sigma squared greater than or equal to 0.0081 there. Okay. So to test this, I'm going to use this test statistic here. And again, this is valid if I have a normal population. And again, we would really want to check that on those 12 data points, look at their QQ plot. But assuming that's okay, our test statistic here this quantity follows a chi-squared distribution with degrees of freedom equal to n-1. Okay, and my rejection region or you could alternatively look at the decision rule, but I'm going to draw out the rejection region here. So right skew distribution. I've got a left tail test here, so I'm going to have a rejection region that is in the lower tail of the chi-squared distribution here. So I'm going to look at chi-squared, I'm going to call it L, and the associated area under the curve to the left is going to be the alpha quantity. Alpha here was, let's see if I remember, alpha is 0.05. So I'm looking for chi-squared with a left tail area of 0.05. Okay, that would correspond to a chi-squared percentile with a right tail area of 0.95. I'm going to need to know my degrees of freedom. Again, the degrees of freedom here is 11. So I'm going to go to the chi-squared table. Here's our chi-squared table. Degrees of freedom 11, but I'm looking for the right tail area to be 0.95, so I'm going to be contending with this this second most right column, 0.95 here, and the right tail area is 0.95, and the percentile is 4.575. Okay, so 4.575. Let's write that on here. That is my threshold. If my chi-squared value is less than that, then I'm going to reject the null and accept the alternative. So this is my rejection region. By the way, it really wouldn't go to negative infinity. Let me kind of redraw that. It would stop here at 0. That would be my rejection region there. Okay. So we need to make a decision. Actually, we need to compute our test statistic. What is our observed test statistic here? The observed test statistic is a chi-squared, and I'm going to give the familiar subscript for observed. Chi-squared observed is n-1. In this case, n is 12 again, minus 1. Times s squared. S was, you recall, the sample variant, or the sample standard deviation from before was 0.047. So I'm going to square that, and then divide by sigma naught squared. Now sigma naught squared in this case is, you could write 0.09 squared, or you could write 0.0081. I'm going to write 0.09 squared in there. But that's the value of sigma under the null, or in this case really at the threshold of the null hypothesis. Okay, so if you compute that quantity here, I actually haven't computed it, so I'm going to type it out. 12 minus 1 times 0.047 squared divided by 0.09 squared. Okay, and I get 2.99. I'd actually have 4 nines there if you wanted to round to the fourth place. 2.9999 is my observed test statistic. That clearly falls in the rejection region. So when I get to make a decision, that part, we would reject H naught and accept HA. Okay, what does that mean in the context of this problem? That means that, well, we have strong evidence that that sigma is in fact less than 0.09. That in fact that's true, and that in turn the standard, the acceptable standard is met for this particular manufacturing procedure. So I'm going to make a statement to that effect. We have sufficient statistical evidence that the bolt diameter standard deviation is in the acceptable range. That is, it's less than 0.09. Okay. And so that is an example of the chi-square test on a population variance here. And I just want you to connect this with the confidence interval result that we had from before. If you look at the confidence interval result, now we had a two-sided confidence interval here. Notice the two-sided confidence interval that it is to the left of 0.09. Even the upper bound is less than 0.09. And so even using the confidence interval, you would reject this null hypothesis here. Okay, so there's a connection between confidence intervals and hypothesis tests. I want you to continue to be aware of that. All right, next we're going to look at estimation for test and comparing two population variances.